Yeah, I want to talk about and Redshift and algebraic theory, and I omitted the words chromatically localized. So I'll try to explain what all of these words mean. I'm going to try and do this from more of an algebra / number theory perspective and less of a homotopy theory perspective, although there's going to be a lot of homotopy theory, but that's not my background. So feel free to just stop me whenever and ask whatever clarifying questions you would like. So let's start with something that does not require any homotopy theory, which is the zeroth K group, just as a warm-up. So I'm just going to give you a definition. Let R be a ring. For now, I don't even need that it's commutative. Then I can consider the collection of all finitely generated projective R modules. So like I'm not going to write this in the notation, but they're finitely generated up to isomorphism. And well, this is, you can direct sum modules, and direct sum of projectives is projective. But this is, of course, not a group, because you cannot subtract, but there is a formal operation, so abelian groups fed into commutative monoids, and there is a left adjoint called the group completion. You can just apply this group completion to this commutative monoid, and this is what we define as the zero K group of R. You may wonder what this operation does, so let's do one example, a basic example. So if R is a PID, so for example, the integers or a field, then if we want to know what K0 of R is, well, in a PID, projective implies free, and we are looking only at finitely generated, so we only have one for each integer, classified by the dimension, and the group completion is the integers. Okay? And another example, generalization of this, is that if R is a Dedekind domain, then K0 of R, so we still have the invariant, you have a map to Z, which, like I mentioned, but you also have another copy. So these are the free, but you also have another copy, is the Picard group. So this was the zeroth K group, quite easy to define at the very least. And now I'm going to talk a bit about homotopy theory. So why am I going to talk about homotopy theory? So in this construction, we took projective R models, but we quotient by all isomorphisms. In particular, we forgot about automorphisms that projective R modules might have. And I would like to remember this information. I would like to carry it around with me, kind of like if you like stacks, for example, just like kind of seeing the stack information in this collection, which means that I want to consider not the set of projective R modules up to isomorphisms, but rather the groupoid of projective R modules. And for reasons that I will clarify later, I would actually like to consider infinity groupoids. And in the end, the K theory will come to us as a spectrum. So I would like to motivate both of these constructions. And I will not give any formal definitions because they're quite involved, but I will give two different sets of intuitions that I hope can elucidate what's going on. So let's see another source of groupoids. So let's say that X is a topological space, which I only care about as a homotopy type. Okay? And I want to try to approximate X, or rather its homotopy type. So the first thing I can do, I can consider pi0 of X, which is the set of connected components. Right? And this is like a zeroth order approximation of X. But another thing I can do is I can define a fundamental groupoid. So this is one groupoid, a group known as a groupoid, known as the fundamental groupoid. And what is this groupoid? So its objects are just points in X, and the morphism from X to Y is a path starting at X and ending in Y. So like maybe I should write hom from X to Y is this collection up to homotopy. Okay, and maybe more familiar is the fundamental group and not the fundamental groupoid, but if you take an object here, namely a point of X, and you look at its automorphisms, this precisely recovers fundamental group. And this construction continues. So you can consider I2, for example, X, it's the fundamental two-groupoid. So in a two-groupoid, you also have morphisms between morphisms. So instead of considering this, objects are still gonna be points in X. One morphisms are gonna be again like paths. But instead of considering them up to homotopy, I'm gonna remember the homotopies. So I'm gonna have maps from this squared, and then I'm gonna take these up to homotopy. All right, and this I can do for any n, right? I can just continue with this process and ultimately get at infinity groupoid. So, and an infinity groupoid is a theorem that an infinity groupoid precisely captures the entirety of the homotopy type of X. This is not going to be important for us, but I hope that this is at least a motivation for what an infinity groupoid. Okay. And let's go back to our case of projective R models. So in our case, we had this collection of projective R models, but I want to consider it as a groupoid. And so recall that before I said that you can direct some modules, but in fact, you can also direct some maps, right? You can just direct some maps between a pair of, like you can direct some a pair of maps. And so this is a groupoid that is endowed with this summation operation, okay? And so I could do the same formal kind of construction. So I can look instead of abelian groups, which is where this thing lives, right? It's in L. I can look.
So the second homotopy group you reconstruct with also is some sort of automorphisms, or
I think what you need to do is to take the automorphisms of the constant path on your point. Like if you have a point X, you can take the constant path on X, that's a point in the endomorphisms of X, and you take its automorphisms. All right, so I would want to form a category in which my K-theory would live, okay? So I'm gonna consider, instead of abelian groups, I'm gonna consider abelian groups in this infinity groupoid, okay? I will soon remark on why I care about this infinity and not just one. And this is, by definition, what is called connective spectra. And now I want to give a second line of intuitions about it. So it's very closely related to derived categories. I'm just going to list some facts about it. So one fact is that if you look at the derived category of some ring, say of the integers, then inside there's the derived category of those that are non-negatively supported. Right? And in fact, there is a formal operation that takes you from this category to this category. Right? You have the shifting operation and it goes in one direction, but it's not invertible from the other direction. You can just formally invert it. And in a similar way, you can form a larger category in which this sits as the connective objects. Okay? So there is a formal procedure that takes you from here to here and similarly from here to
I
here.
think that would really appear over there as like C-alg group like an S, where you wrote ab groupoid infinity. C-alg group like in spaces, is that what you mean?
Yeah, ab is group like community monoid.
Yeah, so ab is ab, oh, wait, right.
Sorry.
Like ab, C-alg as in like,
But is I just
primitive algebras up to coherent higher homotopy.
I mean this. I just don't want to be too like. I don't want to stress the details too much. You need to know how to define these community monoids. Like it's not super trivial what this even means, and you need to do this infinity categories. But I'm trying to hide everything
Yeah,
out of
no,
the
but
room.
still, but
No, but you
better say
you
things
mean
are
like
true, though.
because you have tensor problem, but you don't
Right.
assume that R is commutative, right?
Sorry, maybe I didn't.
I mean, when you say ab, you don't mean literally abelian groups in the sense, you mean like commutative algebras in the sense of, never mind. I get it.
Infinity algebras.
Yeah, infinity
With respect to the Cartesian symmetric
Yeah, yeah.
monoidal structure on groupoids that are
Yeah,
group-like. This is what I formally mean, but I think like in the end, these are just a certain kind of functors from tensor finite sets, satisfying some condition, but I don't want to be like too pedantic about the details. Okay. But I'm not going to give you too many details about the construction, but at least you can get a flavor of what they are like. So this is one thing. Another thing is that if I have an abelian group, then there is, of course, an operation which takes it to an object in the derived category of Z, right? By just placing it in degree 0. And in the same way, I could take it into an object in spectra. So of course, this assembles into a functor from ab spectra. Okay. And there is also a way to go in the other direction. So if I have now an object of the derived category, then I can form its homology or cohomology, same thing for me, as a graded abelian group, right? And in much the same way, there is a functor taking a spectrum and giving you something which is called the homotopy groups of A, but in fact they behave more like homology or cohomology groups, okay? And less so than homotopy groups, but this is the standard notation. Another thing is, maybe I'll make some room. So the derived category has the derived tensor product. And we have a similar structure for spectra. I don't know if the pen is too good or the eraser is too bad. So on the derived category, there is an operation called the derived tensor product for which the unit is the integers. And in a similar way, the spectra, there's a tensor product that I will just denote by tensor product. And there is a unit object which is called the sphere spectrum for reasons that are not important for this talk at all, but it's denoted by this. The last thing I wanted to say, which actually connects the two, is that, well, so now if you have a tensor product in some abelian category, then you can start doing algebra, right? You can define modules, you can define rings, you can define modules, and so on. And if you take an ordinary ring, so like not a derived, just an ordinary ring, and you can consider it as a spectrum, so like via this functor that I mentioned before, what you actually get is an algebra here, so a ring spectrum. And it is true that if you look at modules over R in spectra, then this is nothing but the derived category of R. Okay, so maybe from this perspective, this category of spectrum is kind of providing you a base that sits even before the integers. Okay. All right, so this is everything I wanted to say about homotopy theory, and now we can go back to algebraic theory. So with this in mind, we are ready to define the full algebraic theory. So R is still a ring, and now I look at proj R as a one groupoid, right? It's a groupoid, but I consider it as an infinity groupoid. Just consider it as such. And it has this direct sum operation, which makes it into a commutative monoid inside this category. And this category of spectra, which is the abelian groups, sits inside, and there is a left adjoint, which is I just denoted by the group completion. So I apply this group completion, I get a spectrum. It's a connected spectrum, but whatever. And this is what I define to be K of R, and Kn of R is gonna be defined to be this pi n of K of R. Okay, and so why do I care about the infinity group? Well, so the idea is that this group completion functor is kind of like when you have a derived functor and you start with something that is concentrated in 1 degree, but you apply some arbitrary derived functor, you might get something that is supported on infinitely many degrees, right? It might leave the heart. And this is kind of what happens here, except that the group completion is not a derived functor. In the sense that it's not even between abelian or semi-additive categories or something like that, but it is between semi-additive, not additive. Anyway, it's not a derived functor, but it's almost something like that. So in a way, this is supported on 2 degrees, right? It's a groupoid, so it has like the set of connected components and the automorphisms, and you take the group completion, and then it becomes concentrated on infinitely many degrees, at least a priori. Right. And in general, these K groups are very difficult to compute. So we said some things about K0, but here is an example that is due to Bass-Milnor-Serre. Just to give some more taste for what's going on. So let's say that L is the number field. And so we already know what K0 is of OL. Right, it's gonna be Z times direct sum to Picard, but K1 is gonna be the units. And another example is, so from these examples, we already know K0 of Z is Z, K1 of Z is Z mod 2 by this result. K2 of Z is also Z mod 2, but K3 of Z is already something quite wild, is Z mod 48, and K4 of Z is 0. It was only proven in 2000, for example, so it's quite a difficult result. And in fact, there is a conjecture, which I have no idea what it says in the original formulation. It's called the Van Leeuwen conjecture. Maybe some of you know it. But it says that K4n, like an equivalent formulation, is that K4n of Z is 0. And so, for example, K8 of Z, 0 was only proven by a bunch of people, 2018. So like, these are in general quite difficult to compute. And maybe another thing to say is that they, as you can see, encode quite intricate arithmetic information, right? Like the group of units, the Picard groups. So for example, these are related to special values of zeta functions. So like, these are kind of delicate arithmetic constructions. And as another manifestation of their arithmetic flavor, I want to state the Quillen-Lichtenbaum conjecture, which is nowadays already a theorem of Voivodsky and Rost. Right. And what it says is the following. So let R be a suitable ring, and suitable here, commutative. Or maybe I don't even need commutative, I don't know. Regular, Noetherian, finitely generated, but there are various variations. Like this is proven in some cases. So for example, regular Noetherian finitely generated works. But what is important is that I'm gonna work away from the characteristic. So in which P is invertible. So you choose some prime and you need it to be invertible in the range. Then there is a spectral sequence, and if you don't know what it means, it's fine. I will say something about it in a second. So the spectral sequence starts with the following data. Starts with tau cohomology of R and I'm gonna take with coefficients in V mod P and all of its Tate twists, it's gonna live only in even degrees. In odd degrees, it's gonna vanish, and then in the even degrees, it's gonna be like the corresponding Tate twist. If you don't know what this means, it's fine. Don't worry too much. And it's gonna converge not to K theory, but rather, because I took mod P here, it's gonna converge to K theory of R mod P, then homotopy groups. So some remarks. So a spectral sequence, if you don't know what it means, you start with this data, and then you perform some operations, and you get this data, roughly. But in these operations in the middle, you take sub-quotients. So in a way, it's like an upper bound. Okay, you can only like make it smaller. So you can think that this is related to this in the sense that this is an upper bound. Okay. Second remark is that it's important to take this mod P before taking the homotopy. In general, it's like exactly the same thing as taking a derived cokernel. Is that what it's called? Like cokernel in the derived sense. In general, you're going to have a long exact sequence connecting different things. So it might like shift things between 2 degrees, but so it's quite close to taking mod P outside, but there is some discrepancy. Yeah, and what I forgot to say, and is extremely important, is that it does not converge to this. Rather, it converges to this only for degrees that are large enough. So like maybe the first, and actually this is exactly the dimension, like the degrees is the dimension of R, maybe +1 or something. So it converges to this up to a small finite range, okay? Which is, I think, wild. Like it's such a weird phenomenon, and we will later understand where it's coming from.
Is there some statement without taking the pi star?
Yes, like in the end, like this is some shift in the motivic category, and this is it's associated graded. Like at talc homologies, it's associated graded. But and like after some more operations that we need to do on algebraic K theory, I will be able to say something more later. But okay, so sorry. No, I don't think so. I think like you have the Postnikov filtration of K as a motivic if, and the filtration is motivic mod P's K twisted. And this filtration gives rise to a spectral sequence. But I might be confused. But maybe we can try to figure this out after I finish. So this leads me to the next topic, which is the topic of descent. We will return to this soon enough. And I promise descent in the title. So, the liver. So K theory, as we saw, is like extremely difficult to compute in general. And one way to compute invariance is using descent. So like breaking a problem into various, hopefully easier problems. So here is a descent result due to Thomason. I'm going to state first something weaker, and then state the following, the full theorem. So K theory satisfies Zariski descent. So I didn't define K theory for schemes, but only for rings. So I will state it in the geometric way just because I think it's easier to understand. But let's assume that these are all affine schemes. Because then everything I will say is defined. So if I have like a cover, X is U. Sorry.
Isn't this actually Thomason and Trobau? It's that article, right?
I think it's the other paper.
Okay.
I'm gonna cite 2 papers of Thomason. One of them is with his dead friend. Yes. So
I just wanted to hear that. That's all.
yes. So what the theorem then says is that I can construct K of X from K of U, K of V, K of their intersection as a pullback. So this is a pullback square. in spectra. And again, you need to do this before taking pi star. It's not true that pi n is going to be a pullback, but it's almost like there's a long exact sequence, again, connecting this to the direct sum of this, then to this, then to this minus one. So it's like
Maybe the theorem here more is that this is well defined or something, right? Since you haven't actually defined the K-theory of a non-affine scheme.
that's why I said affine.
No, but the theorem then, but X isn't affine, it's X affine.
I'm assuming everything is affine, just so for this to be defined.
Okay, okay.
But
In other words,
this
it's a-
tells you that you can extend K-theory to non-affine schemes. Like this says that it makes sense to define it for arbitrary schemes in a way. Okay.
But presumably, I mean, the other paper of Thomason doesn't talk about spectra, right? It's probably in a different language or?
I don't remember how he states it. I don't know. Anyway, he in fact proves something stronger. So he proves not only Zariski descent, but rather Nisnevich descent. I wanted to state this just because it's easier to state, but I'm assuming almost none of you knows what Nisnevich is, so I will tell you something. So Nisnevich is, first of all, it's between Zariski now. And what is a Nisnevich cover? So first of all, it's a Natal cover. It's a Natal cover that satisfies an extra condition. What is the condition? So you need that for any x in x, there exists some point mapping to it, some u in ui, when u is mapped to x, such that the map on residue fields is that what it's called? Is an isomorphism. Okay, so this tells you that it is a tal minus Galois extension. And this is precisely what it means, and it's like formally true that if you satisfy Galois descent and Nisnevich descent, you satisfy a tal descent. And notably, K-theory fails to satisfy Galois descent. So, in what sense? The warning is that there are L and L prime fields, okay, where this is a G Galois extension, such that the map on K-theory. So this is how homotopy theorists usually write this. This is not an isomorphism. So you cannot recover this as the fixed points of this in the appropriate derived sense. Okay, not. And this ties back to this peculiarity because here there is a tal homology, but it does not satisfy a tal descent. Exactly because of this failure. And this leads us to the next topic. So how can this be remedied? And this is the second time I'm going to talk about homotopy theory. So I'm going to talk about chromatic localizations. So a very useful paradigm in algebra is to break problems into primes. So you have something, and you can study a specific prime and then another prime, and in the end you glue the results. And this is, of course, let's say that just for simplicity, let's say that everything is p-local. So I threw away all information which is not like rational p. I threw away all added information. Just for simplicity, everything you can state it in a way, but just for simplicity. So in this setting, this decomposition into primes is controlled by this relatively simple space. So it has 2 points, right? There's the point 0, the point P, and the topology is such that this is the specialization. Okay. And then, so one manifestation of this idea is that you have a p-local abelian group. Then A is the pullback of its rationalization, the completion, But then you need to glue them, and the way you glue them is precisely via this information. So you first take the p-adic completion, and then you take the rationalization. Okay. This is like one manifestation of this breaking problems into different primes. And then you can now start and do this in spectra instead of in abelian groups, okay? And this theorem holds as is, like if A was a spectrum, you can rationalize it, you can p-complete it, this whole thing makes sense and it just works, okay? But the surprising thing is that you can further refine this, okay? So in spectra, you have a further, like it's a richer decomposition into primes. And how does that go? So the result, so this is a theorem that's called the fixed subcategory theorem. So like this theorem specifically is due to Levinat, Sopkin, Smith, but these are ideas of Morava and Quillen and Ravenel and many other people. So the analog of Z in spectra is this unit of the symmetric monodal structure called the sphere spectrum, and I can look at its p-local variant. And all of a sudden, this breaks further. So I have 0, and then I have other ideals. This is just a name for a point in this space. It does not mean like an ideal generated by 2 elements. So I just don't have a better notation in mind. And there are infinitely many of those, including one at infinity. And there is a similar decomposition story. So more specifically associated to any such point, this I will also refer to as P0, it's just common to all the P's. This is why it is not, this is just rationalization. The P completion is where you're supported on all of this, and this like further breaks it. So to any such point, I have.
I just forgot, can you give a hint? What are the points actually?
So I'm going to say something which might help you. So for P completion, for example, I have the P complete abelian groups. And in a similar way, for any such point, there is a localization of the category. It's denoted as PTN. It also depends on this prime P, which is implicit in the notation. And so these are like P-complete abelian groups. And there is a functor which is like P-completion. It is called PN localization, although it behaves like completion and not like localization. It's just because it's like it works for other things as well. So it's a general formalism. And this number n, all the height. For reasons that are related to formal groups, but this will not be too important. And actually, these exist only for the finite height, so not this one. But in a way, this entire lecture does not depend too much on what happens in the infinite height, although there is some information there, but I will completely neglect it. Yeah, so as I said, if you want to support it, all of these heights, then this is exactly the P completion, and then you can start like refining it step by step and glue the results in the end. Okay, so maybe I'll write it. Board, and I think it would be nice to keep the Quillen Lichtenbaum. Just to be a bit more concrete with this. So again, at height 0, so like this T0 is just rational spectrum, which is the same as the derived category of the rationals. And at higher heights, it is what it is. I'll give you an example of an object here. If you don't know what any of the words mean, it's fine. It's just, if you do know, then it might help you. So if you have some field L of characteristic P, and you have a one-dimensional formal group of height n over it. Then there is the Lubin-Tate deformation theory of P. And you can just do the same deformation theory instead of in classical rings, you can do it in ring spectra, okay? And what you get is some object, which I will denote this, and it happens to be Tn local. So if you apply Tn localization to it, you get the same thing. And it also satisfies that if you take its zeroth homotopy group, which is like its zeroth homology group, if you prefer to think about this, this is the ordinary or classical Lubin-Tate deformation ring, like this with vectors of L, U1 to UN minus 1, if you know the story. But if this is more confusing than helpful, then it's fine. Okay, so this whole phenomenon of breaking into more and more new primes is something that is completely new to spectra. So it does not appear, like you don't have it in the derived category of any ring, like this decomposition. As one manifestation of this is that if A is an abelian group that I consider as a spectrum, then LTN of A is 0 for any n that is at least 1. Okay, they're just completely not supported. They're only supported at 0 and in a sense at infinity. Okay? And there is a very interesting theorem of Mitchell, which says the following. So let R be an ordinary ring, ordinary in the sense that it's on the ring spectrum or something. Okay. Then LTN of K of R vanishes too, but only for n which is at least 2. Okay? And it is supported at 0 and 1 very often, essentially always. Okay? So somehow K theory sees these higher chromatic heights, but only one of them for ordinary. And let's leave this here. There's another theorem of Thomason, so maybe I can just leave his name. I think this is not the one that's trouble. I think the other one was his friend. So yeah, so this relates it back to et al. To this failure. So the functor. So you can take K theory, and then we know that it is only supported at 0 and 1, like T0 and T1. So you can take T1 local part, and this satisfies Galois descent. And because of what I said about the Nisnevich descent and Galois plus Nisnevich implies et al. Okay? And in fact, he proved more than this. I think he proved it. So this is the et al. Schiffification. So it's not only an et al. Schiff, but it is the Schiffification of K for P invertible rings. Okay? And an immediate consequence of this is that you have such a spectral sequence. So we can actually say it for ZP instead of Z mod P, like you could do something similar there. So there is a spectral sequence, and this time it just converges exactly to LT1 of K of R. Okay? So if you know this, and you don't know this one yet, okay? You don't know this one yet. So this tells you that you can translate Fulden-Liffenbaum conjecture to the statement that the map from pi star of K of R, pi star of LT1 of K of R, is an iso or a star large enough. Okay? Because this is a spectral sequence converging to something accurate, and you know that it's supposed to converge to something else, and they agree for large enough degrees. So these days in homotopy theory, at least, people translate Quillen-Lichtenbaum into these kind of statements.
Oh, is that statement is still part of Thomason? The convergence of the spectral sequence? The first
I don't know if he wrote it, but it definitely follows
Goes
from
back
what
that
he
far.
wrote. Okay, and this leads me to my next to final topic, which is Redshift.
What happens to quotient by P?
So I did a p-completion version. So I do need to take a p-completion here probably, or definitely p-localization. I must have the p-localization, but I think it suffices. I don't think I need p-completion. Maybe, I don't know. So like you can definitely do the mod p version, but it's you can just do mod p to the n, and this works for mod p to the n, and we can just assemble them. Yeah, I think it is in his paper. He stated in a slightly different way. Instead of writing T1 localization, he writes inverting the bot element. But it's exactly equivalent. Okay, so my next topic is Redshift. So we've seen all of these very interesting phenomena. So Mitchell tells you that K theory of something that is supported at height 0, so for something like classical, can touch height 1, okay? But nothing above it. And we've seen this Thomason theorem that tells you that if you look at the highest height at which it is supported, then you have better descent properties. Okay? And we also have this Quillen-Lichtenbaum conjecture, although like there are variants of this, but I will not touch upon it. Okay? And well, one thing you can do is, so K-theory, as I define it, as the group completion of projective R modules, just works for ring spectra instead of rings, same definition. And it's very natural to like put other ring spectra in there because K-theory is a spectrum. So it kind of makes sense to try to put other ring spectra. And of course, there are many interesting ring spectra to put inside. For example, you can take K of R and do the K-theory of it. This is something you can study, and we know some things about it. And then in the early 2000s, in a bunch of talks and papers, Azani and Rognes made a web of conjecture which I will colloquially call them the Redshift conjecture. Now they had one of them specifically they called the Redshift conjecture, but I think nowadays we kind of refer to the entire thing as the Redshift conjecture or the Redshift philosophy. And roughly, like nowadays when people say Redshift conjecture, what they usually mean is something like that. So that if you take something that's supported on height n, then K-theory of it is supported on height n+1 and perhaps all of the heights below, but does not vanish at height n+1. And also some things about descent. So the last few years have seen remarkable progress. Like we basically knew nothing till 2018, and now we know essentially everything for commutative rings. So I will state two theorems, and they are prove them. You need to combine works of Lan, Matthew, Meyer, Tamed, and another paper by Clausen, Matthew, Newman, Noel, and then another paper by Berkland, Schlank, Yuan, and actually another paper by Yuan, but is already here, although Matthew appears in both of these two. So if you combine like all of the theory of them, you get the following. So K-theory increases chromatic height by 1, but we only know it for commutative rings. So let R be a commutative ring spectrum, which is Tn local, and non-zero, then the Tn plus 1 localization of K of R is a non-zero. Okay, this is this part. And the M localization is 0 for all higher. And this is this part. Yeah, so this is known nowadays for all commuted rings, which is like super exciting to people in homotopy theory. This was one of the biggest open conjectures.
What, I mean, I'm confused. If R is not commutative, I mean, is K of R even a ring?
No, but you can still do the Tn localization. K theory decreases your commutativity by 1. Like if you have an En algebra, then you get an En minus 1 algebra. But you can still get a spectrum. And the second theorem that I want to state is something of this flavor of the Galois descent. So the theorem is that Tn plus 1 localized K theory satisfies Galois descent for finite P groups. So not for all finite groups, but at least for P groups. In what sense? So that R S be a G Galois extension. So I have an action of G on S, exhibits this as a Galois extension. Tn local things. I think here we don't even need commutative. And G, I assume, is a finite group. Then, so precisely what I said that does not hold in general does hold. So we have this map from K of R, the fixed points in the appropriate derived sense. This is a nice one. Okay. So this is precisely a theorem of this flavor, but only for finite P groups. Okay. Oh, sorry, I forgot to say here, Tn plus 1 localization. Very important, because we know that this is not true in general. Okay. So in a way, what this theorem tells you is that if you, so K theory of R is in general supported between heights 0 and n plus 1, right, by this theorem. And the things below height n plus 1, they don't satisfy them. Like we have examples where this is not satisfied. But if you concentrate on the top one, then it is satisfied. So in a way, in fact, the top one is the simplest one. Some formal way also. But also in a way, it's controlling most of the things by...
Where's this Galois descent though? I'm kind of trouble seeing what this is. In what sense is this Galois descent?
You have something and you can take the fixed points outside. Like this is alternatively like K of S fixed point origin. You take it outside. Yeah. So this is Redshift.
The P is like before, I mean, it's invertible in.
So no, I don't need it to be invertible, but in fact, so these rings are Tn local and Tn depends on P. So this is implicit in all of the notation, which is super confusing. But P is not invertible. In fact, it's the opposite situation. These rings are in particular P complete because Tn localization factors through P completion. So this is in a way kind of orthogonal to what people do in ordinary algebraic theory, like with the height 0. And this is what is very fascinating about this, that somehow you're away from characteristic 0, yet you see phenomena from characteristic 0 arising here. Like, usually you prove these things using the fact that P is invertible. And here it is P complete, like if you invert then you lose most of the information in a way. And in the last 10 minutes, I will say something about results of Tomer, Schlank, Carmeli, and Yanovski and myself about what we call cyclotomic Redshift, and also applications to the wow, this is terrible. Telescope conjecture. So in our paper, so this is joined with Carmeli, Yanovski, and our main theorem is actually a generalization of this for things which are not groups, but rather like higher groups. But I will spare this from you and rather talk about two consequences of our theorem. Okay? So let's say that I have an ordinary commutative ring, or just commutative. Then I may consider the cyclotomic extension, just like adding, like looking at arc x and dividing by the cyclotomic polynomial, and this behaves well away from P. For example, then it is a V mod P to the K star Galois extension. And badly at P, for example, if you work, for example, for RFP, this is totally ramified, right? So behaves in a much nicer way away from P. And surprisingly, so like this construction is something where you, like, it's very unclear how you would even define something like this for ring spectra, because taking quotients in general is very complicated for rings. And even taking Rx, there are variants of this and it's unclear what you would want to do. So it's a priori unclear how you would even try to do something for this. For ring spectra, not to say the least about like behaving well. And surprisingly, there is a construction for T and local rings. So this is something that is due to Carmeli, Schlank and Yanovski. So for a T and local ring, there is a ring which we denote it this way, but we also put n here because the construction depends on this height. Okay, it's not something that is like uniform in any way in the height, and it is a Z mod P to the K star Galois extension of R. Moreover, like it has a working theory of cyclotomic extensions. For example, you have Kummer theory, you have a discrete Fourier transform, like you can do many of the things you can do with classical cyclotomic extensions with this very peculiar variant. And then we have the following theorem. So this is like a consequence of our main theorem. So let R be a local ring. Then, so one thing you can do, you can look at this cyclotomic extension. And you can take its K theory. Then Tn plus 1 localize the result, which I remind you is the interesting height for K theory. Like it's the highest height at which it is, the highest height at which it is supported, because I assume that this is Tn local. And on the other hand, you can just take the K theory. And then this is a Tn plus 1 local ring, so you can form the height n plus 1 atomic extension. Our theorem is that although these are completely different constructions a priori, like there is this construction is not uniform in the height, there is an isomorphism like this. Okay. Moreover, it is of course going to be Z mod pk to the star equivariant, like it respects the action. And just note that, for example, just let's think about the case k equals 1. Then this is a Z mod P star, namely CP minus 1 Galois extension. So this tells you that it takes this CP minus 1 Galois extension into a CP minus 1 Galois extension. And in fact, it tells you which one. So it is a strengthening of this theorem, or maybe not, it's not incomparable, but like it's related to this theorem in two ways. So first of all, not for P groups, it's for a prime to P group, or in general, it's going to be like mixed. It's going to be P to the K minus 1 times P minus 1. And it is not only like telling you that this is the same as this, but rather it tells you exactly what is the Galois extension you get on this side. So these are.
Sorry, can you just add a pair of parentheses on the right-hand side? Thank you.
Okay. So you might not care too much about this, and but there is a very interesting phenomenon that you can observe in this case. So let's say that you have you can consider the case of the infinite cyclotomic extension. You can go to k equals infinity. So in ordinary algebra, if you have a Galois extension, even a pro-Galois extension, an infinite one, it is always faithful. You cannot take a module over the base, enter it up, and get 0. This is just not true in higher algebra. This is precisely related to phenomena of hyperdescent, if this does fall to you. Okay.
Let's ask about the previous one.
Yes,
I mean, so it says there is this ring.
No, let it R be a ring.
No, just before that. I mean,
This is a construction.
which is, I mean, can you characterize it by some properties or?
It's a construction, like you take this ring, you do some operations. It is a functor for them. So it's a construction. In homotopy theory, these kind of things are.
Okay, so my actual question is there like an obvious map, at least in one of the directions here in the theorem? Or?
No, but there is a not so obvious, but not so not obvious map between things that involve, like are involved in this construction, and you kind of see that all the different parts fit. How, and we actually do this not for rings, but for categories, and this helps in the construction. And anyway, so what I was starting to say is that if you look at the infinite extension, so this is a ZP star Galois extension, but a priori, it is not faithful. So you might try to take the fixed points here. You may take the fixed points here, and you get a map from here to the fixed points, but it just might fail to be an isomorphism. And in fact, it fails in, like, this is kind of the point that I'm heading to. Yeah, but there is an extra condition that you can put on R, which guarantees that it is an isomorphism. So if R is what is called Kn local, so Kn local means Tn local plus local with respect to this Lubin-Tate spectra that I mentioned before, so where this is of height n. So this is a variant of Tn local, okay? The further subcategory, and you can do this whole primary decomposition with respect to this, and a priori get maybe less information. But the interesting thing about them is that they're way more computable in general. Tn localizations are way more computable than Tn localization. And one of the things that you can prove for this, we actually like they actually prove this first for this, and then it follows for Tn local spectrum. That for them this folds.
When you say faithful, you mean that the.
I mean, faithful means what I said before, that if you tensor, then
Tensor what?
a
Tensor
module
module.
over R with this, you may get 0. But this is equivalent to this being an isomorphism. Okay. So this is like a theorem of Bartel, Carmeli, Schlank and Yanovski. And if you combine this with this fact, you get the following result. So that R be T and local, so I'm not assuming that R is K and local, I only need that it's T and local. But now I'm gonna consider the Kn plus 1 localization of K. Okay? I'm gonna consider Kn plus 1 of K of R. Okay? So by this result, I know that I can add the height n plus 1 roots of unity and then take the fixed points. And I get this back. But by this theorem, I can put them inside the extension, not the fixed points. So this tells me that I can compute this by first adding roots of unity inside the unity of height n, but acting the groups outside. Okay, this is what happens if you combine this and this. And this is interesting because this is the first instance known for hyperdescent for K theory localized at higher heights. And the other reason that this is interesting is that in an independent paper by, I should finish, by Berkland, Han, Levi, Schlank, they gave counterexample for the Tn plus 1 local variant. So like if you try to prove this with Tn plus 1 here, this fails. And together, this tells you the Tn plus 1 localization not the same as Kn plus 1 localization, which was the subject of a long-standing conjecture known as the telescope conjecture. And this is one of 2 ingredients in the disproof of this conjecture. Okay, I better finish now.